Hi everyone, we are Group 5. My name is Anna Perez and I'm an electrical engineer.
Hi, my name is Jasmine Abraham and I am an electrical engineer.
Hello, my name is Giovanni Garces and I'm a photonics engineer.
Our demo highlights include object detection and distortion analysis, real-time optical capabilities, and alert and haptic feedback system.
For the optical system, we're going to start with a 650 nanometer laser. We're going to have a 6mm focal length expansion lens. We're going to have a 68mm focal length collimating lens. We're going to have transmission grading to create the 6-stripe pattern. And then at the bottom, in here we have the ESP32 cam. In front of the cam, we have our 650 optical bandpass filter.
Here we have our 2 ultrasonic sensors, our speaker on the side of the box for optimal hearing ability, our main PCB design board for all of our components to plug into, our audio amplifier, our DF player is in the back, our ESP32S3 vroom, our battery, and connected in here is our vibration driver and motor. The SightSense system combines 2 microcontrollers, 1 camera, 2 ultrasonic sensors, and multiple feedback modes into one compact wearable. It continuously monitors the environment in front of the user and translates spatial data into immediate, meaningful feedback.
Next, I'll explain the electronic subsystem built around our custom PCB. The board hosts the ESP32S3, which serves as the main processor for the device. It handles sensor fusion, timing, and the entire decision-making logic. We integrated multiple components directly onto the PCB, including the DRV2605 haptic driver, the DF mini player audio interface, and the PAM8302 amplifier, and the necessary power regulation circuits, the 3.3 and the 5-volt regulators. The board also includes I2C and UART routing, noise reduction filters, and property matched signal traces to ensure stable communication across all modules. Compared to a breadboard setup, the custom PCB gives us cleaner power regulation, lower electrical noise, especially important for audio, and more consistent digital signaling. The compact design also makes the system more reliable when mounted on a wearable surface.
For our vision subsystem, we're using a 650 nanometer laser diode as the structured light source. The beam first passes through a 6mm focal length expansion lens, which slightly enlarges the beam to properly fill the aperture of the next stage. After that, it enters our 68mm focal length lens, collimating lens, which straightens the beam and produces a uniform projection suitable for long-range detection. Once collimated, the beam hits our diffractive optical element, which generates the structured light pattern we'll use for depth reconstruction. This pattern is optimized for ground level detection and spreads across the user's path. On the sensing side, we're using an ESP32 cam with wide angle M12 lens to maximize field of view. In front of the camera, we've added a 650 nanometer bandpass filter to isolate the laser illumination and suppress ambient light, which improves accuracy of feature extraction during outdoor operation. Overall, this optical chain allows us to reliably project and capture a structured light pattern for real-time obstacle detection in our wearable system.
Stop. Obstacle very close. Turn left.
Here in this demo, we're testing SightSense in the Creole building hallway while Gio walks like a normal user with the device on his leg. As he approaches the trash can, our system detects the obstacle using the laser grid and ultrasonic sensors, and you'll hear the audio alert say obstacle detected, close, turn left. Next, as Gio continues walking, SightSense picks up the camera person as another obstacle and gives the same type of clear audio warning and guidance. As he walks further down the hallway, the system is constantly reading distances to walls and doors and updating the LCD screen in real time so the user always knows how far obstacles are. When Gio gets very close to an object, around 0.50 meters, the device adds a strong vibration pattern so the user can physically feel that the obstacle is very close. With all of these working together, audio alerts, distance, and vibration, SightSense helps visually impaired users detect obstacles early and move more safely and confidently. In this video, we showed an example of a real-world scenario of two people walking past the SightSense. You can see that it picks up both movements and saying that an obstacle has been detected.
In this scenario, we demonstrate how the system detects obstacles at different distances as Jasmine walks forward. The system begins tracking at 2 meters, and once again she gets within 1.5 meters, it sends the first alert. As she continues moving, another alert triggers at 1 meter, reminding her that she's getting closer. When she reaches 0.5 meters, the system gives a directional instruction telling her to turn. Here, the system detects a tree ahead and tells her to move left. As she walks along the grass, it continues monitoring her path, then picks up the person recording the video, prompting another turn to avoid them. Finally, the system detects the tree again and repeats the instruction to turn left. Throughout this example, you can see how the system identifies different types of obstacles and guides the user to safety. In this test, we walked directly toward a pillar while the device continuously measures the distance using its front-facing sensors. As we approached the obstacle, the system generated both audio alerts and vibration feedback in real time. At a farther distance, the device plays an audio cue saying obstacle detected and gives a slow, gentle vibration pulse to let the user know something is ahead. As the user moves closer, the alert escalates to stop and right or left. The vibration becomes more rapid and intense, clearly signaling that they're very close to an obstacle.
Here you can see our structure light pattern projected on the ground. On the computer, we're streaming the live camera feed from the ESP32 cam with the 650 nanometer optical bandpass filter, capturing only the laser pattern for clearer detection. And finally, this is where the camera will be placed on the lower leg of our final wearable design.
In this screen recording, we're showing how our optical setup can tell the difference between a clear path and an obstacle using the laser grid pattern. At the start, you can see the undistorted grid projected on the floor, and our model classifies this as unknown or undistorted because there's nothing blocking the pattern. Around the 15-second mark, we place a chair onto the grid, and you'll see the pattern bend or break. Our model now correctly flags this as distorted, meaning an obstacle is present. When we remove the chair, the grid returns to normal and the model goes back to unknown or undistorted. We're still actively training and improving this model, but this video clearly demonstrates that our system can clearly already recognize both distorted and undistorted grid patterns in real time.
Here we show the calibration pattern under ideal conditions. These first 8 frames are completely undistorted, giving us a clean reference for comparison. Now we transition to the distorted set 8 frames where the pattern is warped or shifted. These examples highlight exactly how distortion appears and why accurate detection is important. The engineering requirements, which we will be presenting, include high detection accuracy for multiple forms of obstacles, including people, walls, trees, curbs, ditches, drop-offs, and steps, greater than or equal to 90%. The distance of obstacle detection in front of the user should be up to 2 meters, and we should have an immediate response time between obstacle detection systems and real-time alerts less than or equal to 250 milliseconds.
Here we're showing how well our system can actually recognize obstacles in front of the user. We tested 10 different objects including people, trees, walls, poles, and columns, and in every case the system should have detected the obstacles. Our device successfully detected 8 out of 10 obstacles, only missing 1 tree and 1 column. That gives us an overall obstacle detection accuracy of 80%. This tells us that the system is generally reliable at recognizing a variety of real-world obstacles while also highlighting where we still need to improve our detection algorithms.
Here we're showing quantitative results from our chair distortion test. In this clip, we labeled each frame as either distorted or undistorted based on whether the chair leg was bending the laser grid pattern. Our model was correct on 32 out of 39 samples, or about 82% accuracy. Most of the mistakes happened during fast transitions, like when the chair was quickly moved into or out of the frame, or when the chair was present but not actually distorting the grid yet. Even with those edge cases, these results show that our optical model can reliably distinguish between distorted and undistorted patterns for the chair, and we're continuing to train it to reduce those transition errors.
Firstly, we're showing 8 frames of the calibration pattern in its undistorted state. These clean, stable images serve as our baseline for evaluating image quality and tracking. Notice how the pattern remains consistent from frame to frame with no bending, stretching, or warping. Now we transition into the distorted set. These 8 frames demonstrate how the pattern changes when distortion is present. You'll see shifts, bends, and irregularities that break the uniformity we saw earlier. Comparing these two groups clearly illustrates the difference between undistorted and distorted conditions and why reliable detection is essential for our system.
On this slide, we're showing the distance detection data from our LCD screen. We tested objects between 0.5 and 2 meters away and compared the actual distance to what the sensor displayed. Across 8 trials, the largest error we saw was the 0.08 meters, and the average error was about 0.04 meters or 4 centimeters. This tells us that within our 2-meter operating range, the system is accurately measuring the distance and displaying reliable values to the user on the LCD. This slide shows our response time testing for the shin-mounted obstacle detection device. We recorded 5 runs while our participant walked toward a tree acting as the obstacle, shown in the photo. For each distance trigger, the system generated audio cues, and at closer than half a meter, it also added vibration feedback. The table lists the exact times when each event occurred and confirms that in every case, the device responded in under 250 milliseconds. That means the user hears obstacle detected or stop and feels the vibration almost instantly, giving them time to react safely in a real outdoor environment.
We're proud of the progress we've made and the potential SightSense holds. Thank you for watching, and we hope our work inspires continued innovation in assistive technology.